One of the first programs I wrote was a calculator where you could input two numbers and an operator to apply between the two, where it would spit out the result. Now this quite clearly is not a good calculator. It doesn't even evaluate expressions with two operators, let alone arbitrarily as many. Wouldn't it be nice if you could give the program a simple mathematical expression and it would spit out the result like a real calculator does? As it happens, this problem is much harder than the easy one operator thing. If you're using an interpreted language, you may have access to an eval function which could possibly do this for you. But you wouldn't be able to add features that most common math expression evaluators may want, like implicit multiplication and expression manipulation and so on. In this video, I don't just want to show the code being written, but I want people to actually get some intuition about what exactly is going on here, and also lead you guys to actually inventing this process yourself. Looking around at existing tutorials, honestly, none of them really helped me intuit what was happening, so I do hope to change that. Okay, before we actually evaluate some expressions, we need to know the steps to getting there. How do we actually evaluate these expressions if they are just strings? Well, with just strings, we can't do it. We need more structure. In fact, commonly, there's 3 separate passes that happen on these input strings, each of which introduces more and more structure to the data until the final pass which gives us the correct answer. Let's take a look at these and why they are there in the first place. Okay. Here we have 2 expressions. Wouldn't you agree that both of them should evaluate to the same value? So it seems like whitespace is completely irrelevant to our current problem. We can also see that there's these logical units in these strings, like the number 50 and the operator plus, and another number 22. These logical units are commonly referred to as tokens. A token has a type, plus, minus, star, slash, number, open parentheses, etc. And a lexeme, which is the underlying string for the token. For example, 22 is a number token with 22 as its lexeme. If you're using a manual memory management based programming language, these lexemes don't need their separate allocations, but can easily be just a view string into the input expression string. This first pass converting our string to a token stream is called a Lexer or Tokenizer. So let's implement one. The Lexer itself can hold 2 pointers, start and end, which will be a span inside the input string that represents the current token. When lexing a token, we first skip whitespace and set our start and end pointers to the first character that isn't whitespace. Then we can make sure that we are not at the end of our input. If we are at the end, we return a special marker token called EOF or end of file. After this, we can move ahead the end pointer by 1 character, and depending on that character, we can switch into a few different tokens. If the character was an operator, we can return a token with the appropriate type. If the character was a number, we can skip all the following numbers. If we see a dot there, we skip that, then skip more numbers. After we are done, we take the current span and return a token with the type of number. Similarly, if the character was a letter, then we skip all the alphabets and numbers after that point until we hit whitespace, and then return a token type ident token. Ident, by the way, stands for identifier, which pretty much means some name. That's pretty much for lexing. It's super easy. What I do want to get into after this though is what happens to these tokens after being generated by the Lexer. Technically, at this point we can evaluate our expression. That is, we can iterate through our token stream by doing something like get next token, make sure it's a number, get another token, make sure that's an operator, get another token, make sure that's a number, do the thing based on the operator and get a new left token, then repeat until the end of the token stream. However, this has a big problem. As you can probably guess, it literally doesn't care about the order of operations. If multiplication is to the left of addition, it's fine and dandy. Multiplication will be carried out first. If it is the other way around though, well, it's just wrong. This is where we would want another structuring step, the second pass in our pipeline, called a parser. There are plenty of types of parsers out there, but the one that I will be covering in this video is called a Pratt parser. But before I get into explaining the parser itself, we should look at what it outputs because it's quite interesting. So yeah, from the title of this section you might have guessed that the next step of structuring outputs a tree. But why tree? Well, let's make sure we are on the same page about what expressions are. Expressions are anything that produce a value. For example, 5 plus 4 is an expression. But we aren't bound by needing an operator there. In fact, just the number 5 is also an expression. What this tells us is, well, expressions can be made up of other expressions, just like a tree that can be made up of smaller subtrees. Expressions can be terminal, like leaf nodes, or non-terminal, like the branches in a tree. Isn't that cool? This tree of expressions is commonly referred to as an abstract syntax tree, or AST for short. Anyways, back to our evaluator. Before we look at how this token stream to AST conversion happens, I want to take a look at the final part of this whole system. I want to do this for a specific reason, which I will explain in a bit, so bear with me for now. Okay, so first of all, we need to represent AST nodes in some way. To do this, I'm using a simple tagged union that looks like this. If you're not aware of what a tagged union is, I'll link the Wikipedia article in the description, but it's basically a sum type in C. You can also use inheritance or something else to model a node. The node type here denotes what the node is actually representing. So if the type is a number, I will set the node's number field and set its type to node type number. Other types are add, subtract, multiply, divide, and the positive and negative nodes. Once we have our AST, to actually see what it evaluates to boils down to a very simple recursive function. Basically, since we have established that every subtree in this AST itself is an expression, all we have to do is evaluate each leaf node, then use those values to evaluate the upper nodes, and so on until we reach the root of the tree. So, this evaluate function looks like this. A switch based on what type of node it is, and then doing the appropriate thing. The number nodes are always leaves and will return their own values. Other nodes, like the binary operators, will evaluate their left and right subtrees and then apply the operator on the values. Let's take a look at this example tree. Here, to evaluate this tree, we call evaluate on the root. The plus node will first try to evaluate the left 3 node, which will directly return 3. Then, the plus node will try to evaluate the right star node. The star node will try to evaluate 4, which returns 4, then evaluates 5, which returns 5. Now that star has 4 and 5, it will multiply them together to get 20 and then return that. Finally, the root plus node has both its left and right answers, so it will just do 20 plus 3 and return the result. This is the final answer of our input expression. From this, you should see one major thing. The lower the subtree is, the sooner it will get evaluated. So why is this important? Well, we want certain operators to be evaluated before others. So we can enforce that by making sure that those sub-expressions are lower on the tree. Now, armed with this new info, let's step back to step 2, the parsing. Okay, let's build up to a working parser by trying to understand how it works. The parser itself needs a bit of context. It will store a Lexer which will provide it tokens on the fly. Technically, you could have a full pre-parse where the text gets converted into a token list, but you can also tokenize exactly when you need to, which I find to be good enough. The parser will store just one token, which is the token we are currently looking at. Just to make sure we are on the same page here, whenever I say we advance the parser, I basically mean that we move on to the next token by calling Lexer next token. The easiest expression to parse would be just a number, like 10. I'm putting this in a parse number expression function because I'll be reusing it. We can take a look at the current token and output a corresponding expression node with the type number. Accordingly, we can parse and set the number field in the union. Let's not forget to advance to the next token. Now, let's do the actual work in Parse Expression. For a working implementation, we need to formalize this order of operation thing. To do this, we associate every binary operator, that is, an operator with left and right operands, with a corresponding precedence value. A higher precedence value denotes that an operator has to be evaluated sooner. So, the precedent of star has to be higher than the operator plus, since multiplication is done before addition. Also, it should be less than the precedence for the caret operator, since exponentiation happens before multiplication. This is perfectly modeled by a simple enum, where I can define enum members to correspond to term, multiplication, division, and exponent in the right order. We also have to include a minimum precedence, which I'll explain in a bit. The map from token type to precedence can be expressed with a simple array, since the token type is just a number. See a special syntax for this, which is super nice. Okay, let's now go deeper on how we would implement the parse expression function. Say we have two new operators that we invented, alpha and omega, with some precedences. Looking at a generic expression with these two operators, a, alpha, b, omega, c, what would the tree look like? Well, we really have three cases to check in this case. The precedence of alpha could be greater than the precedence of omega, the precedence of alpha could be equal to the precedence of omega, and finally, the precedence of alpha could be less than the precedence of omega. In the first case, since the precedence of alpha is greater than the precedence of omega, it obviously has to be evaluated first. That's what the precedence is actually telling us. You should recall at this point how we represent this in our tree. If an operator is to be evaluated first, it should be lower on the tree. So in the end, the tree for the first case should look like this. Case 3 is the exact opposite of this. Alpha has to be evaluated after omega, so the tree will look like this.
As for case 2, well, think about what equal precedence actually means. It means that we need to evaluate these operators from left to right. If we think about what tree this corresponds to, well, here we go. It's exactly the same as case 1. So what we can do is merge cases 1 and 2 together into the same code path.
Okay, back to the implementation. Since we need to compare two operator precedences to figure out the ordering in the tree, the parse expression function can't only take in a parse context, but also the precedence of the previous operator. This function is going to be recursive, and it isn't the easiest to understand how it works. The easiest way I found to conceptualize it is by coloring an input expression. For example, take this expression. The first parse expression call is supposed to return us the full tree of the expression, so we have to color in the entire expression. Within this call, when we encounter the first star, we see that we have gone from a lower precedence level of plus to a higher precedence level of star. This is case 3, and what we do when we encounter case 3 is we recurse. We basically want to evaluate this whole block of higher precedence operators, then return that to the plus as its second argument. This second parse expression call will go on until we hit the case 1. That is, we see the plus after the star here. When we do hit case 1, we return out to the original parse expression function. But wait, before that happens, within the second parse expression call, we'll encounter another case 3 and then a case 1 with the caret operator. Along with this, after the plus, we again dip to a higher precedence level, which will be another parse expression call. So, basically, when we encounter case 3, we will recursively call parse expression again with the precedence level of the operator that comes before it. And when we come across case 1, we return out to the previous parse expression function that came before. Case 2, as I said, will do the same as case 1. Now that we've seen how the expression gets colored, we can further reason about what the precedence that we pass to the parse expression function is actually doing. You can say that it is setting up boundaries for the call, saying where it should stop passing.
So here, if we pass in the precedence term, then the parser will not go beyond the plus operator. Similarly, if we pass in the precedence of factor, it will not go beyond the star operator.
So finally, after understanding all this, we can write the core logic, the parse expression function itself. First of all, we have to start by parsing a number. The next token will be an operator, which we will store for now. We can also store the precedence of the next operator by using the array lookup that we preferred before. Now we have to do a loop. Why a loop? Well, remember our example expression. We will be returning to a parse expression function multiple times. We don't want to stop at just one sub-expression, we want it to work with arbitrarily as many. This is where the little trick about having a lowermost precedence comes in handy. In the enum, precedence min is 0. In a precedence lookup array, anything that isn't explicitly mapped to a precedence is automatically mapped to 0, that is, the minimum precedence. So, comparing a token's precedence with precedence min is the easiest way to know whether the token we find is actually a valid operator or not. This can be the first exit condition of our while loop. This is where we will have to implement our 3 cases, or 2 rather, since cases 1 and 2 are in the same code path. Case 1 is it if current operator precedence is greater than or equal to next operator precedence, which is our return to previous call case. So we can just break out of the loop. Otherwise, we have to do a bit more. Firstly, we'll have to advance past the operator token. Then we reassign the left variable to something returned by a new Parse Expression function, which takes in a few arguments. We'll look at this function in a bit, but all it is supposed to do is build a new node after taking in the expression which is to the right of the current operator. After this, we reassign the next operator to whatever operator the parser is currently on, and reassign the precedence variable to the new operator's precedence. After all this, at the end of the function, we can just return the left variable. That is it for the core parse expression function. We're basically building up the left node more and more until the full tree is generated. So what does this parse expression function do? Well, it simply will allocate setup and return a node after parsing the right hand side of the operator. So let's write that out. We have to switch over the operator type to figure out the type of the node. We set the left node as is passed into the function, but for the right node, we have to call back to our parse expression function. The binding precedence we pass in will be the precedence of the current operator. But this isn't it for the parser. We also want to allow expressions in parentheses, so where would that code go? Well, we need to think about what parentheses even do in an expression. It's pretty much a way to not disturb any surrounding precedence in the tree.
So here on the left, we can see that with the parentheses, only the number node changed to the subtraction node, whereas on the right, the entire tree had to be regenerated.
If you notice, in an expression, you could replace any number node with a parenthesized expression. So anywhere we call parse number could simply be replaced with parse parenthesized expression. So what we can do here is insert a middle call for parsing a terminal expression. The reason I call it a terminal expression, even though some of these will not actually be leaf nodes, is that the overall tree isn't changing from this node. So let's write this function. So here all we have is an if-else chain, checking the current node and doing different things based on that. If the token is just a number, we can immediately just parse a number. If it is a parentheses token, then we can parse another expression, then advance the close parentheses. If we get a plus, we know it is the unary plus, which means it is the identity function basically. If we see a minus, then it's just a negation. The interesting part here is that for numbers and unary plus and minus, we need a new type of node, but not for parenthesized expressions. In the end, all that the parenthesized expression is doing is inserting expression nodes in places of leaves, so it doesn't need to be demarcated specifically. Also, in the parenthesized expression parsing part, we are giving the parse expression function a precedence of min. All this does is removes the artificial bounds that get inserted otherwise, and is exactly what our top level call for converting a string to a tree will look like. We should also handle the case where none of this happened, and we'll just output an error node. I won't cover error handling in this video because it's already probably too long of a video, and also because there's a lot of techniques that can be used for handling errors. Finally, after all of this, we can return the ret node. We have finally finished the full pipeline for an expression evaluator. Passing any valid string should give us a corresponding output if we run the resulting parse node through the evaluate function. There's one more thing I would like to add here though, and that is support for implicit multiplication. Functions like eval in JavaScript or Python don't really handle this, so this outlines how powerful parsing things yourself can really be. Implicit multiplication works on any terminal expression, where we just have to collect all the terminal expressions that are next to each other and multiply them together. So, just before returning our ret node, what we can do is check whether we find an open parentheses or a number token. If we do, we can build a synthetic multiplication node, with the left node being the current terminal expression,
and the right node will be the next expression that gets parsed. We pass in the precedence of factor here so that we can leverage our previously existing structure to allow for using the caret operator in the implicit multiplication. And that's it. The evaluator now supports pretty much everything that a simple calculator allows you to do. So, to recap, firstly, we take in the input from the user and then convert it into a token stream to get rid of unnecessary whitespace. Then, we convert this token list into an abstract syntax tree to accurately model what an expression actually is. Then finally, we run through our tree, evaluating each node from the leaves up to the root to get the answer. Now, here's a kicker. Both the first two steps of this whole pipeline are exactly how compilers and interpreters start off, where source code is taken in, lexed into tokens, and then parsed into an AST. After this, the compilers and interpreters do their own thing, like optimization passes and other things, but that's the story for another day. As usual, the code for this project will be linked down in the description. We also have a community Discord now, which you can join. That being said, that's all for today. See you next time.